So this talk is a combination of things that we've done in the past and moving up into the present, and it works so well with if you were just in the same session and heard the talk right before me, they are so complementary. So I'm super excited to have a conversation with the folks from Fernleaf. So today, I'm from UNCW. I teach GIS. I've been there a long time. I recognize a lot of people in the room, so I'm glad to see new faces and familiar faces too. So to get started, UNCW is trying to launch a new collaboration with our Southeastern North Carolina community on a resiliency hub. And so we recently had a workshop, and I can send you all results from that workshop. But I think what you'll notice from today's talk is that it's really important to, just like our previous speakers, to combine the technology with people and get out there, have conversations, have community involvement, have professional involvement, because it just makes these projects more robust, more sustainable, and more impactful in the future. So the structure for my talk is really these four things. I'm going to sort of briefly cover why there's a water crisis, the need for understanding the flooding process. I'm going to talk about some geospatial approaches to assessing risk and vulnerability in this community engagement that I mentioned. And then I'm going to focus on a method called AHP. Can I see a show of hands? Has anybody heard of AHP? All right, it's a new thing for everybody. Excellent. Okay, and then how that can be used to assess the flood hazard and make predictions. And then I'll wrap it all up with some conclusions. So the World Water Crisis is a launching a new map called the World Water Map. You can see the link here. It's a combined effort between National Geographic and Esri. And if you haven't checked out that website, it's quite phenomenal. It's a worldwide effort, but it's a beautiful story map that if you ever need to share with the community the importance of thinking about water, I encourage you to check that site out because it really introduces the topic really nicely and makes that connection between water as a resource, as a hazard, and the people that are affected. So what is a water gap? A gap is calculated as demand that's greater than supply. It's a really simple concept. If you have more demand for any kind of water resource, whether it's drinking water, agricultural water, industrial water, and that demand is higher than the amount of supply, which is the supply is computed from different sources, but predominantly any surface water or shallow aquifer is considered available water supply, and deep water aquifers are non-renewable because they just take too long to replenish. The gaps are worldwide. You can check out the website, and it shows you across the world on a granular level, but rather coarse, how things have changed through time from a supply and demand perspective, where these gaps are the greatest, usually in very high populated areas that have a high demand. But from those three predominant uses, agriculture, industry, and people, residential. There's another app that you might be interested in looking at. It's from the Living Atlas. It's called the Water Balance app. And it shows you, again, on a grid cell approach, how the balance is playing out between soil moisture, precipitation, snowpack, runoff, and evapotranspiration, and how this balance has been changing through time. So it gives you a little bit finer resolution perspective than the previous app. It's sort of zooming in a little bit better. And you can also, at each time you click or interact with the map, you can get very detailed information about the rainfall events, catastrophic events, etc. So it's another one of those apps you might want to use, say, at a community event to help explain what the issues are with these resources. Looking closer at flooding in particular as the hazard in the US, it is the leading cause of damage. Just in the US alone, with that high flood risk, there's 4.3 million homes impacted. In North Carolina, just between those dates of 80 to 2024, there were 117 confirmed weather or climate disaster events that led to over $1 billion each in damage. Here's a map showing the nationwide perspective on flooding. This is from the FEMA repetitive flood claims data. Zooming in closer on that data, you can see that North Carolina, now this isn't flood risk, this is the amount of claims, right? This is the amount of FEMA claims just for flooding impacts. So it's a problem, and this is a great sort of segue into how do we address these issues, right? How do we address flooding in particular? So to address this, we kind of need to look at the different types of flooding. So there's three main, there's actually a fourth, groundwater flooding, that's not as big a concern per se, but also the three main ones are fluvial, which is basically from rivers or streams or lakes that are overbanked which leads to a big flood event, or it can be a really fast flash flood event. So time is different with these different types of scenarios with fluvial flooding. It's a very common flood approach with respect to hydrodynamic models. The second flooding event is pluvial, and this is a storm that's independent of our water bodies and streams. It is when drainage is overwhelmed and we have flooding across the landscape that's separate from a fluvial flood event. And then along the coast, we have these coastal inundation, storm surge, high tide or sunny day flooding. And what you see in this graphic is river flooding across the US through time. And the black triangles are showing a significant increase in riverine flooding. What do you all think of that map? Do you think it's correct? It's all in the Northeast and Midwest, showing a significant increase in fluvial flooding. Do you think we just talked about North Carolina, it's had an increase in flooding, right? So why do you think North Carolina is increasing in flooding if it's not fluvial? Probably pluvial is having a big impact, right? We're a growing state, we have a lot of people moving here. That could be the number one reason. Along the coast, here's a map showing different flooding quantities through time, where the days, so the chart to look at, I realize it's probably it's dramatically hard to see, but if you see where the blue graphs are, that's where there's been an increase in coastal flooding events. Predominantly on the East Coast, some in the Gulf, less so on the Pacific. Any ideas why it's more coastal flooding on the East Coast, on the Atlantic? Well, it's stormy, and it's also subsiding, good, and sea level rise. Okay, excellent. So the main factors for creating a fluvial event, again, is to have rainfall. So that duration of rainfall, the intensity, and the spatial extent of rainfall is the key factor. This will lead to a rate of change in the water level in our water bodies. And then, of course, the changing drainage characteristics all impact how much water is getting to these water bodies. So the flood risk itself is a combination of the hazard, this flood hazard, with the vulnerability. The physical factors that make out the hazard can be changing, and that can lead to increased hazard. And of course, the vulnerability can also be increasing if we have more population growth or land use development. And then importantly, we need to think about that this is a complex problem, that things have changed through time. We've had a really complicated history of our land use through space and time, and that all plays into how vulnerable places are, whether it's infrastructure vulnerability or people vulnerability. So again, to wrap sort of things up into this concept of what are the flood factors, we have the hazard, which is the actual flood event. The exposure or vulnerability, those two terms are usually both used from that perspective. We have a lot of development in more affordable but higher risky locations. We can have a loss of habitat as we build more. We can increase this impervious surface quantity across our landscape, and that can lead to an increased problem. And this is the same graphic that we saw in our last presentation that talks about the process for becoming more resilient while we think about hazard, vulnerability, and our changing landscape. But it's pretty complicated. This is a slide showing you some models that are out there, some different approaches that have been taken from the private sector through the public sector. And I don't know about you guys, but it's really hard to keep up with all these models out there, right? It's really hard to keep up with all the tools, the web apps, the new data that's coming out, the different models. It's really complicated. So our hope, right, is that we actually develop a nice comprehensive list of which tools are great for which purposes. Here's an example of one. Here's the Climate Hazard Resiliency Tool. It's geographically not that informative at the granular level, but at the tract level and county level, you can get an assessment through time of how it's changed for all of the different hazards. So again, this might help you inform and help the folks from Fernleaf also help inform their communities. Here's an example of the data that has recently been released on high tide nuisance flooding. This is a brand new data set, and that's why I'm showing it to you, because anything that's new that's coming out is really informative. So you can combine that with all of your other data to really look at where is the risk happening. Here's the coastal flood exposure mapper data. It goes pretty far inland. It doesn't, it is a coastal tool or coastal data set, but it does inform the entire coastal plain on how exposed the landscape is to flooding. And then maybe this is a new one to you, but Google just released their Flood Hub. Anybody see this? It's a worldwide product, which is what Google and the Google Enterprise team is all about, developing worldwide solutions, because they have vast amounts of data that they can do that. But if you zoom in on these data, you can get at a little bit more granular level where you can see, if you click on each one of those data points, you can see what they have as far as water, potential flooding, hazard sort of scenarios. This is a flood alert system, and you can see there at the time when I took this snapshot that there's only a few sites up in the Northeast that were experiencing flooding. But this is predominantly publicly available data. Probably 99% of that's USGS stream gauge data. As I mentioned earlier, rain, precipitation, is the key variable, right, for predicting flooding. How many of you in the audience are like, oh, I got to deal with rainfall data? It's an enormous problem, right? I see some hands going up. It's a big problem. It's really difficult to deal with. I don't know if you guys have dug into the NASA archive and trying to predict rainfall. It's really hard. It's a huge amount of data. It takes a PhD to figure out how to deal with it and bringing it into a GIS for your modeling. Here is one source for you where it's predicted for the whole US, different scenarios. It's still granular, it's kind of coarse, but it could inform your models if you're going that direction. And it's a really easy data source to implement in your GIS. Another one is from NASA called I don't know if it's supposed to be pronounced a certain way, but the Global Land Data Assimilation System has pretty high spatial resolution data for multiple different factors when it comes to rainfall, and it's directly importable into ArcGIS Pro. And so there's lots of different thematic layers in this data set that you could implement in your models. But I just thought maybe people in this audience haven't seen this product and you might want to implement it in your flood risk scenario kinds of models. So let's talk about a few case studies. The first one is looking at land use development along our coast and how does that relate to flood risk. On the left are the building permits that were issued during a certain time frame. These were aggregated to these hexagons. These hexagons were then compared with the rate of building development in each hexagon. So the brighter the red, the more rate of increase in development in those areas. That was then combined with flood potential derived from a LiDAR data set to look at more of a pluvial impact, right? Where are depressions where water can start collecting? And then you put those two things together and you can compare the vulnerability to a flood with urban growth, and you can see in red are places where they are both urbanizing, high growth, and have high flood potential. And then here is another map showing which places are less developed versus which ones are more developed and are within in a floodplain or within a 500-year floodplain and have a lot of depressions. So these data are really informative at the local level for planning and preparing their resiliency planning efforts. The second case study is a project funded by NASA looking at combining an investigation of chronically underserved or disadvantaged communities with the propensity of the landscape to be enhanced through green infrastructure, either as a landscape level type of green infrastructure or at the property level. So coarse big projects like a huge park, right, versus at the property level, installing green infrastructure like rain gardens. We all know the importance of green spaces. They provide lots of ecosystem services that help the economy, that help the people, that help the landscape, etc. So the chronically identified vulnerable areas were through this model you can see at the bottom of this slide. It incorporates many dates of census data, many census variables to look at chronically high underserved areas. Those areas were then identified and reached out to see where people would like to have community events to talk about flooding and to talk about possible solutions through green infrastructure. These workshops were conducted at 4 locations. You can see the green infrastructure model where the high dark green areas are amenable or good for green infrastructure. And we conducted those workshops. They were fantastic. We used this wonderful Living with Water toolkit, if you've never seen it. And the results from that project are outstanding. Everybody is on board right, in these 4 communities to install more nature-based solutions. The next case study is about a model that's taking place in Burnt Mill Creek where we're installing sensors because there are not enough water level sensors out there, and working with schools and working with the community to help build an alert system for this Burnt Mill Creek area. Again, I can't hit community engagement enough. And then lastly, the next model is this AHP, and I talked about it, and I know you want to run to your 11 o'clock session. I know I'm like desperately trying to get this in time. So if I run out of time and you have to run, please reach out to me about AHP. This is a model, it's the analytical hierarchical processing method that I'm literally implementing now. It's in our classrooms. The students are each doing one of these watersheds that's outlined in magenta. Here's the data that's being collected. On the left are all of the data sources. All of these data are being processed to produce variables that are indicative or important according to the literature for flooding. Ultimately, those flooding risks assessment is going to be compared to the extents from Florence and Matthew. These data were then all processed to produce 10 standardized variables. Those 10 standardized variables were run through band collection statistics to produce a matrix that tells you how much multicollinearity is going on in those 10 variables, so you could rerun your model by removing a variable that might be too collinear with another variable. And then you produce this matrix. It's all in Excel. And then on the lower right, you all see that black box around that right column. There's your weights. So how many of you have done a decision support model where you just weight variables? That's all this is. How do you get there is by comparing all of those 10 variables and deciding as a group in a room, like I did with my students, with your community members, which variable is more important. So there's the AHP matrix. see right down the left side, it's the same 10 variables as across the right. The green area is where you compare them. And you say, is elevation more important with respect to flooding than slope? And every community might be different. It depends on your topography, it depends on the watershed. So you decide the weights using that green scale on the left and the red scale on the right. If it's a value more than 1, then you can see right how it's written, and you enter the value into those green cells. That's all you have to do. It's a paired comparison approach. And voila, the matrix builds itself out automatically. It's all calculated for you, and you get this average, which is the weight. You can also compute an index that tells you whether or not there's some confusion between how you've related those variables. But ultimately, that matrix can be used to help determine the weights, and that matrix is a collective thing. People in the room can discuss it and say, no, wait a second, I think elevation's more important than slope, or whatever your variables are. You can just instantly rerun it and get your weights automatically. It's super fast. Once those weights are computed, you run it through your raster calculator. It's a really simple raster calculator. You then compare it to you compute your hazard, compare it to your event, and you can create maps like this. So on the left is your weighted model that was 95% accurate according to the weights that were in that AHP. You can rerun the model and say, I don't want to put any weights on it. Make them all equal and test the accuracy. And in this case, it was only 85% accurate. So in conclusion, I love community engagement. We need more monitoring. We need more live data. We need to keep testing and improving these kinds of modeling efforts. And I can take some questions. We have a few minutes. Any questions? I'm sorry I'm so short, and you were like, who's the mystery person behind the podium? Yes.
Could you repeat again what AHP stands for?
Analytical, the question is, what's AHP? Analytical Hierarchical Processing. So I had a really brief slide that had 1 million citations just to illustrate the use. There are at least 40 papers right now that have come out in the last 2 years using this method. It's very popular. And it's not that hard. Don't think, oh my gosh, I don't want to do it, it's too hard. Yes?
So the biggest difference between AHP and other models is that you can talk to the community and get these new weights faster.
Yes, it's essentially a really fast way of doing multi-criteria decision analysis.
As if before it would take a whole other process and then come back a week later.
Exactly. That's a really great question, because there's a new widget. Are you all using Experience Builder to build your web apps? There's a new widget that allows you to do instantaneous weighted overlay analysis, where you can just say, okay, here are the AHPs, here's the weights, and rerun it instantly on the web. So you don't even have to be in the room together. You can be on a Zoom and say, hey, let's rerun it how you want to rerun it, and let's see what your results look like. So it's very fast. Yes?
You mentioned, I believe, a particular toolkit that you could bring to community meetings that was helpful.
Yes.
I wanted to ask, looking at that matrix and all the different parameters that are weighted, it seems like they need some sort of explanation. It seems like a complex topic we the public understand. Is explanation of those parameters included in that, or you have other slides?
Yeah, I probably made that too confusing. So the AHP approach has not yet been used in the community. What was used in the community in that toolkit was which green infrastructure solutions would you like to see in your backyard, in your neighborhood, in your community. So it was that was focused on, is there a flooding problem? And if so, are you supportive of green infrastructure? And if you are, now we're gonna learn about it, which choices would you like to see implemented? So it was all about green infrastructure at those meetings. Yeah, it wasn't about developing the weights.
From the county here, I just wonder what defined your study area, because we're a neighbor, and I'm just kind of trying to understand that.
Which one, for the green infrastructure one or for the AHP one?
The AHP or,
Yeah, so
well, I don't know that I saw Russell County included in any of the study areas. I'm not really sure.
You're right. So this map was used to identify which watersheds, and I did, to demonstrate for the class, I chose this watershed to show them how to do it, but each student in the class is doing one of the pink watersheds.
Okay.
So, sorry, come talk to me and we'll do your county. Or I'll show you how to do it, it's super, if you wanna collaborate on it, I'm with you. Cause I know there's, like, Town Creek issue, there's issues with resiliency
Yeah, we've
along.
had a bit of flooding as well. Yeah,
Yes,
definitely.
yes, I'd love to chat with you. I'm not leaving Brunswick County yet.
Well, I understand that, and I want to finally meet you because you've headed up the intern program, and I want to say hi,
Oh,
I'm Tammy.
oh, hey Tammy, oh,
It's
you
nice
emailed
to
me.
finally
Yeah,
make
yeah.
time.
People are dropping like flies, but I'm happy to stick around and chat.